Okay, thanks for your patience. Sorry about that, a little technical difficulty. Yeah, so it's great to be back. It's been a few years since I've been to India. It's great to be in Mumbai at IC Bombay. So thanks for having me. I've been for years involved with scientific Python, and I guess from the title of this conference, you would imagine this is about scientific programming. And so today, though, I want to talk about something slightly different, which is Python for statisticians. I'm going to have basically two parts to this talk. The first, I'm going to give you a little bit more context for statistical computing in general, the landscape, and then I'll talk in particular about permutation testing, which is something, area of statistics that I'm very interested in currently. So I guess I'll get to it in a bit. So just a history of computing, physics, with a little bit of emphasis on Berkeley. So for a long time, well, statistics is a fairly new field. Almost all of the theory has been developed since the 1820s, 1850s. A lot of it was in the 1900s, 1920 to 1950 period. In particular, most of it was developed by two people, R.A. Fisher and Jerzy Neiman. R.A. Fisher, you may know of, and Jerzy Neiman was the founder of the Berkeley Department of Statistics, and in particular is the sort of the mind behind, along with Egan Pearson, the mind behind hypothesis testing. Although permutation testing in particular, which I'll talk to today, was first introduced by R.A. Fisher in around 1905. Early on, statistics and computing have been intricately intertwined. So statistics started out dealing with a lot of census data, and often that was something where you tried to compute summary statistics. Then at Berkeley, at least, around World War II, the first computers came in. You can see a picture of what I think was probably one of the first computers the department had. This was funded in order to do bombing research during World War II. The first real modern computer was the PDP-11, which came in 1974, which is basically had an original operating system, but became quickly one of the first operating computers in the world to have the Unix operating system on it. I think by that summer of 74. It was a computer that was shared between the math department and the stats department. And then just a little brief history of statistical programming. So even though statistics has been intricately tied to computing, statisticians haven't been the best programmers, and they've not been the most ardent users of programming tools. Although even in the beginning, a lot of the uses of early computers were statistical in nature. So Fortran's probably one of the first programming languages that was used widely by statisticians. And initially what happened was they would basically call different statistical procedures directly in Fortran. And then S was invented sometime around the 70s. In between the intervening years, there was this interesting language called APL, which I believe stood for a programming language. And it pioneered a lot of ideas that are precursors that you see today. So it was the first, I think, programming language that was fundamentally built around an array data structure. So in NumPy, you've seen the array object and the array. Python, or R, is also heavily built around this object. And I just have a keyboard picture here. I think it's interesting. The keyboard for APL they used a lot of special symbols. So if you look here, you'll see a lot of math symbols. In particular, you'll see these little arrow keys. So if you've used R and you're familiar with the assignment operator, it's not an equal sign, it's a little arrow, which was because originally they were taking this APL thing, which had a keyboard, which had an actual arrow on it. But now you use a little caret. Yeah. Okay. So yeah, little arrow keys right here. So that you can now use directions. S was sort of invented originally at 18, just like Unix was. And what it was to do was to help these statisticians who weren't very computer savvy at the time to have a more common environment where they could easily and interactively call a lot of these Fortran routines, which is still similar to what we do today. If you look under the hood at NumPy or R, you'll still find a lot of Fortran and C underneath it there. And so S is still, largely responsible for a lot of the design decision in this programming language called R, which is a free version of S that essentially implemented S, but added some semantics and some other operations, I think, from schemes. And around the same time, this other language, Python, which we are talking about in this conference, was made. So I think Python may have preceded R by a year or two, but essentially they're contemporary languages. The difference being mainly that, well, I'll get back to it. Yeah, so going back, I mentioned that a lot of statistics computing was fairly straightforward. But there's been applications historically and currently that are very intensive, computationally intensive. One of them is Monte Carlo. This is one of the early uses of computers. I've just got a simple example here of just Monte Carlo, so it doesn't show up terribly well, but to implement or to estimate pi, what we've done here is we've just uniformly thrown down numbers and then looked for the proportion that were inside the sphere or inside the unit circle. And so here's just some code here. You can look at it on your own later on. But you can see that you get something fairly close, at least the first few digits of pi quickly. Bit better looking? Yeah, so. Do you want me to do what? Down or up? Down, oh yes. Yeah, can you everyone hear me still? If not, I'll just try speaking up a bit. Yeah, the next thing was resampling. And so we're going to be talking about permutation tests. And again, I mentioned that that was something early on. But R.A. Fisher around 1935, if you've heard of the lady paste and tea experiment, that was basically used a permutation. That was where it was first introduced. Shortly after R.A. Fisher around 1935 introduced them, they were extended, theoretically at least, by Edwin J.G. Pittman. But it wasn't until the bootstrap was introduced by Efron around the 70s that these permutations were revisited, and they've now developed into something that's much more computationally much more interesting. And we'll be revisiting some of that. The other thing I think is more recent, which is deep learning. So maybe some of you guys have heard about deep learning or neural networks. So these are the new sort of best in class classification algorithms. One of the leaders in the field is Joshua Bengio, and David Ward Farley is also a core NumPy and SciPy contributor. He's a grad student of his, and they've got a really nice framework, Blocks in Fuel, which is built on top of another framework called Piano, which are all Python tools. You can go on GitHub and find these if you're interested in that. I'm not going to talk about it today, but just to mention, there's a lot of very computationally intensive statistical applications now. So just to go back to Berkeley a bit, here's some data that I think is fairly interesting. So there's a class now called Statistics 133. It's the Concepts in Computing with Data course, and it's essentially our course. It was introduced in 2004 academic year, and before that, there wasn't a serious computing class at Berkeley. This is still the main undergraduate required computing course. So there's 3 main courses for the undergraduate curriculum. There's a computing course in R, there's a probability theory course, and a statistics course. And you can see here that I've got here the undergraduate majors. And initially, essentially, everyone in the class was an undergraduate major. And also, you can see that there was about 30 or 40 undergraduate majors. And if you went and extended this data back, you'd see that for quite some time, there's been about 30 or 40 statistical majors. But something's really interesting happened recently, which is statistics has become a very rapidly growing field. I believe I've heard that it's one of the most rapidly growing STEM fields. And another thing that's happened, so we've got this increase in undergrads, but if you look at the increase in the number of people taking the Berkeley R statistics course, it's gone up rapidly. In the next year, 2015-16, which isn't over, we're going to have about the same number. These numbers are limited by the number of seats we're willing to offer in the department. So out of Berkeley, we're training about 600 students a year in R, and we could do much, much more if we were willing, or we had the teaching staff to supply it. So this is just to point out both statistics is growing as a field, and also R is very popular. And if you've done some statistics, you know that. So the question I think naturally arises that why am I talking about Python then? Everyone in the stats department at Berkeley is very comfortable with R. Many of the courses have an R component, and then the serious R computing classes in R. So my main thinking about this is, one is that Python really is a general purpose programming language. R was specifically made for statistics. It's based on this language S. The S is for statistics. And also, Python's special in that it has, well, not special maybe, but it has batteries included, so it has a huge number of standard libraries built in that ship with the software. And that includes things for network I/O, interacting with the operating system, working with databases, all kinds of things, graphics. And so if you're going to be doing modern scientific statistical computing, you're going to often find that you're not going to be just dealing with small tables of numbers. You're going to be dealing with very complicated data sets that might require lots of statistical processing. you might have your data in a database. You might want to put up a web interface. And so having to switch from your language that you're using for statistical computing to some more general purpose language is a difficult transition to make. And it's basically also the case that many scientific applications are very heavily Python oriented now. So in neuroimaging, which is a field I was in before, Python is rapidly becoming the main language people use. It's used in many, many other fields. It's used in the computer science curriculum now. The main undergraduate statistics or computer science programming courses in Python. Also, there's just tons and tons of Python courses throughout the campus. You'll find lots of people doing Python. R is still very popular, of course. And there's also now, so Python had originally been driven by the scientific community, scientific Python. That's why we're here. It's not stats and that means that there's tons and tons of scientific applications already available that already have some statistics. And one of the things that I like to see is more sophisticated statistical thinking go into a lot of scientific applications. So working with where the scientists are at and developing those tools, I think, will help that. So in particular, you've probably heard of pandas, scikit-learn, and stats models. I think pandas we did some stuff with, and definitely a few people raised their hand with scikit-learn, with Gael. And stats models, if you're not familiar with it, it's a package originally built on some code by a statistician at Stanford, but mainly driven by people in econometrics now. Another thing, this is the very first year we've offered this course. There's a new course at Berkeley called Stat 94. It's a course that's been jointly developed by the computer science department and the statistics department. There's this vision on campus now that every freshman would have a data science course. Essentially, almost no field is now not heavily influenced by computing. And so that's not just traditional scientific fields, but you go to the history department, and now they have data there. Anthropology departments, literature departments start doing questions about who the author was of different texts, and they might do some kind of literary analysis. So it's just inundating the entire field. So you can see here, Ani Adhikari is the teacher for that class. She is probably the best teacher in statistics at Berkeley. She's an amazing teacher. And so the campus is not only recognize this as something important, but our departments also put one of our best teachers behind it. You can also find the course webpage. It's data8.org. This is from the front page. You'll find on it video lectures and some slides. Also, homework and solutions, I believe, are available. The videos are on YouTube, and I highly recommend you. Adi Adhikari is a really amazing lecturer, and if you've a strong statistics background, she does an amazing job. Another bit about this, which is unrelated to my presentation, is that they decided when they were doing this, instead of dealing with a lot of these asymptotic approaches to statistical inference, they would use resampling methods like the bootstrap and permutation testing. So if you're interested in following up more about what I'm talking about today, this is a great resource with a great lecturer using similar methods. They also, you'll notice, are using Python for this course. So even though R is a fundamental programming language in the department, you're seeing Python at this very basic level for this whole campus-wide initiative, and also using permutation tests, which is, again, what I'm talking about today, coincidentally. I mean, coincidentally, they're doing it as well as I am. There's also a lot more Python in the Berkeley Stats curriculum. These are courses that I'm involved with. So there's a new course that was also this semester on reproducible and collaborative statistical data science. That's a fundamentally Python course, no R at all in it. That also uses Git and Make and a lot of Unix processing, or basic tools. There's two other courses in the graduate. So this is a both undergraduate number and a graduate master's course. These two other master's courses here, the Masters of Statistics capstone is primarily Python, although R is somewhat used. And Stat 243, the Introduction to Statistical Computing, which is our main graduate level statistical computation course, is primarily R, but it also includes Python. So even now, where we have courses that are primarily an R course, the department feels that they can't avoid teaching some Python in that course. And we also have Python courses that are pure Python with no R component. So even though R is really popular in the department, really popular in statistics, I think it's writing this on the wall that Python is becoming an important language for that domain as well. So now I'm going to spend most of the time talking about permutation testing. So here, who here has actually heard of permutation tests before? Okay, perfect. So this won't be too basic. So permutation tests, you also sometimes call them randomization or re-randomization. They're non-parametric, right? So most of the asymptotic results, the way you're able to get asymptotic results is you parameterize your model. and then you estimate those parameters. This is a non-parametric approach. Non-parametric approaches in general require many, many fewer assumptions, which is really good because you don't impose a lot of assumptions on your model because you're going to try to discover something about the data, and you don't want to discover something about your model, right? So if you have a very constrained parametric model and you do some analysis, often the kinds of things you're discovering are really properties of your model, not properties of the world. Unfortunately, a lot of non-parametric approaches require a lot more computation, so they've not been popular until recently, especially when you had to do things. Parametric approaches often have the case that once you prove some mathematical result and you do some experiment, you use some test statistic, you can just look that number up in the table, and someone has pre-computed the table, where in non-parametric approaches, you often have to find those computations each time. And it's for statistical significance testing. So we'll talk about this a little bit, but basically, everyone here is familiar roughly with statistical or hypothesis testing? Can you raise your hand? Okay, so the situation is that you have some kind of null hypothesis, and that's what you believe is the thing that would otherwise be the case. And you want to collect some data, and you want to see if that data has evidence to somehow reject your null hypothesis. So you're doing some kind of treatment, and your null hypothesis might be that the treatment has no effect, and you want to use some experiment to get some data that would give you evidence that would maybe allow you to reject the hypothesis that the treatment has no effect. So you're trying to develop a drug. You want it to have an effect. You want it to help the patient, but you have to assume it's not going to, and then find evidence that it's going to do that. And to do that, you need not only your hypothesis, but you need an alternative, right? So is that it has an effect, and the null would be no effect, and the alternative would be some effect. And we'll see an example of that in more detail. These were originally developed in situations where this property called exchangeability is justified. And in these situations where you'd have exchangeability being justified, which I'll talk about in a moment, what you get is that the conditional distribution of your test statistic, and a statistic is just a function of your data. So you get some data, you take it, and you compute some number. So this distribution, conditional distribution, conditional on your data that you saw of this function of the data, it's under the null hypothesis. It's completed the fact that you can relabel the data. So just to give you a quick definition of exchangeability, it's when you have some sequence of under the joint distribution is invariant under something like a permutation of the indices. So here's the easy way to see it. So the joint probability of these n realizations of these n joint or random variables is equivalent to any permutation of those. So I could first see one value and then another value and another value, or any permutation of those values are equally likely. And so just, whoops. So you might have heard of the phrase IID, so identical or independently and identical, and that's a really core idea, and a lot of intro classes talk about that. So exchangeability, if you have that, you have IID, but if you if you have IID, you have exchangeable. IID are exchangeable variables, but if you have exchangeable things, they're not necessarily identical. So a simple example is if I sample without replacement. So I'm pulling something out and not putting it back into the box. Dealing cards. So if I deal you 5 cards from a deck that's full, and I deal you another 5 cards, all of those individual sequences of cards are equally likely. But once I deal out a card, that deck changes. So I'm drawing the second card from the same distribution, or identical. Or sorry, independent, it's the same distribution. So now I'm going to spend most of the time after I've just give introductory remarks on an example. So here I've got an idealized experiment, and we're going to again look at this effective treatment. In this case, what we have is 11 pairs of rats, and each pair is from the same litter. So we have 11 siblings, right? So I'll just write these down so we'll remember. And each pair are siblings. And now what we've done is for each of those pairs, so each sibling, we flip a coin, randomly flip a coin, and if it's heads, the first sibling is given this treatment. In this case, they're either going to have a normal environment or they'll have some enriched environment. We do that for each of those pairs independently. And at the end of 65-day period, we're going to measure the cortical mass, right? And then the idea is that maybe if you enrich a rat's environment, that their brain will be larger than if you don't. And so what we've done is we've got this data here. So again, the treatment is the normal environment. So each of these are a sibling. So there's two rats that are brother and sister, or brothers maybe. Control is the one that's normal, and then treatment will be the one where we've enriched the environment. And what we're going to do is just take a difference of them. And you can see here that in this particular instance where we've done this experiment, most of the differences are positive. There's some negative. But if you study in statistics or if you've done experiments, what you know is that if I did this again, if I got another 11 pairs of rats and I did this experiment again, these numbers are going to change. Right? So this is a random variable. And so what I want to know is, are these differences significant? And the question, which doesn't show up here, maybe it shows up, is we're asking is how we're going to analyze this. So what does it say? So how should we analyze the data? So you guys, if you take any statistics courses, you might immediately think of some solutions. But let's first just step back and think about our hypothesis again. So informally, what we believe is that the null hypothesis is that there's no effect. So it doesn't matter if we put the rat in an enriched environment or not. And the alternative is that if we have an enriched environment, that should increase the cortical size, the brain size of the rat. Right? So we've got an idea that we might want a one-sided test. So we're only going to be testing, the alternative will only be that it increases. We're not going to be having an alternative that it's a negative number. So now what we need to do with the statistician is that we need to test what we want to do. And I've got some contenders here. So the original one, probably the classic one you might think of immediately, is this two-sampled t-test. And so what you've done is you take all the treated rats, take their mean, so the mean size of the treated rat's cortical area mass, and you take from that the mean of all of the control rats, and then we're just going to normalize this, standard normalization. And this normalization we can show theoretically with an asymptotic result that this distribution is going to be a type of t-test with some number of degrees of freedom. You base that number of degrees of freedom on the number of animals, and then you can just look this up. But instead, maybe a better idea is to use still an asymptotic approach, or a parametric asymptotic result, is this one sample test. So instead what we're thinking is that we don't want to just take all of these differences, or all of the controls and all the treated and average them. Instead what we want to do is take each sibling, find their difference, and then deal with that average difference, right? And the idea is that maybe that these siblings are more homogeneous, right? So if you do a twin study, this is often what you want to do. You don't want to immediately throw away the fact that you've got these twins. You want to first get these differences. And now we've got a one sample because we just have this list of differences. So if we went back to that previous slide, so the is either we take the mean of that group and subtract the mean of that group, or we just take the differences and take the mean of this. So this is the one sample version, and then dealing up here is the two sample version of that problem. And again, it's going to be something very similar. We get the mean again, and we're going to normalize. And this is probably a better idea than this. But permutation tests, I think, are even a better idea, and we'll see a little bit why. So if we use a permutation test on the differences, we're going to be able to calculate this, another way to calculate a p-value, but it's probably going to be an even better way to do this. So let's think about the null hypothesis in a little more detail. Strong null hypothesis is that the treatment has no effect whatsoever. It would be as if the cortical masses are assigned before you do the randomization. So these are some kind of predetermined quantity, and then after they've been predetermined, you flip this coin and you just put labels on whether they're treated or not. But that label has nothing to do with the size of the cortical mass. So then it's equally likely that the rat that has the heavier cortex would have been assigned either label. And so if we think this way, this gives us 2 to the 11th possible abilities. So we've got already these weight differences. But the fact that it was a positive or negative number was just the outcome of the fact that we happen to flip this coin, which has no relationship to the actual size. So that means that each of these plus or negative versions are equally likely. So we've got 2,048 equally likely possibilities. And so for instance, if we go back to the original list, we had mostly positive numbers. I think that 2 was a negative. But all negatives now is equally likely to have been observed as what we did observe. So we've got the situation now where we have equally likely possibilities, and we're going to take advantage of that if we do the permutation test. On the weak null hypothesis, we just say that on average, across the pairs, it makes no difference. And that's that situation that we're going to do with the parametric models. And the alternative is that the individual responds only, or it depends only on that individual's assignment. So it doesn't matter anything else except what you were assigned, whether you were assigned to the treated or the control group. There's a bunch of special cases we could further deal with. And if we did these special cases, we might be able to use a permutation test to get a confidence interval. I'm not going to go into the detail for time. We also might think that there's another alternative would be that there's some interaction term, interactions between how my response depends on other people's assignments. But we're just going to be dealing with this one here. So now let's go back and look at the assumptions of those we had. So the first one, the two-sample t-test, that's going to assume, in order to have the correct p-value for this test, that the masses of each individual rat are IID sampled from some normal distribution. And we don't know the variances, but they're all the same. And there's an unknown mean. And this test will test the weak null hypothesis. Plus, we have to have these normality, independence, non-interference, just some other assumptions. And I could probably spend a lot of time going through those, but there's a lot there. The one-sample test, slightly different. So instead of that the masses are ID sampled, we're going to now assume that mass differences are ID sampled. But still the same kind of thing, weak null hypothesis and all these assumptions. For the permutation test, the only assumption we're going to make is that coin toss that we did, that randomization procedure was fair and independent across pairs. And then it's also going to test the null hypothesis. So the interesting thing about this set of assumptions is that is the only set of assumptions we have on this board that we know are true, because that's how we did it, right? We were the one flipping the coin, and if we have a fair coin and we independently flip, we're going to get exactly those situations that we want. And so the basic idea of these permutation tests is the assumptions you make are going to be the assumptions that you actually impose on the model. So let's look at the calculations and see in practice what happens. So here's the student's t-test. So if you go through those numbers, I've written them up there. You could have written them down and done this yourself. Here's what the mean difference comes out to be. Here's what the sample standard deviation is. Both these numbers are things you can just calculate yourselves. This t-statistic comes out to be this. And you can look up this number on a t-distribution, I guess n-1. So that would be, in this case, 10 degrees of freedom. And so we've got this p-value. And this is often what they report in the literature. They normally don't even report this, which would be the effect size, right? So often in the literature, what you see is just this p-value, and they make some conclusion. But let's just think about this. So the assumption that cortical weights have a normal distribution, why would that be? It's not clear at all. And why the variance of the differences between treated and control will be the same for different litters, it's not clear. In fact, not only are these not clear, but we know some things are not the case. So we know that treatment and control are dependent, because if I assign one of the litter mates to be in the control group, that means the other group is in the control, or vice versa. And so, why should this p-value assume, based on these differences, have this ID sampling from normal distribution? And if we reject this null, why did we do it? Did we do it because there's an actual effect? The assumptions that we had were wrong. Right? So that's the problem with this. So look at the permutation test. In this case, we can do this, and I've got code I'll show you in this moment. So we could enumerate all these possibilities, right? So, essentially, the first possibility would be that, so I'll forget the actual numbers, but, if we could start out with, they're all positives. And so I'll just do 5 here, or maybe I'm going to do 3. Right, so we could assume they're all positive. We could assume that one of them, right? And I can do now 2 of them, all the versions, and then when I finally get to 3, right? So I can just enumerate all those and assign those to those numbers. So I can enumerate them all, and there's 2,000, so that's not too hard for a computer. And then now what I can do is I can take the number of possibilities. For each of those possibilities, I'll compute my test statistic. And this is my observed test statistic. And I'll just see of all likely things, is it the case that my observed test statistic is bigger than the actual possible ones? And then I'll normalize that. Well, you can skip that line here. But if we had more than 11 pairs, let's say we had 100 pairs, we're going to quickly be unable to enumerate them all, but we can simulate. So in this case, we're going to be simulating from the exact distribution. And then simulation, that's just going to be that we simulate for some sufficiently large number. In our simulation, we're going to want to be uniformly distributed, uniformly drawn from our sample population. And then we just count them up and divide by the number of simulations. Okay, so now let's just look at that, what that looks like in Python. What I've done is, you could have done a loop, but I'm going to use the itertools package. So itertools product is going to let me get this information right here. I'm going to put my original data in. I'm going to call the treated group T. My control group I'm going to call C. The difference is D. It's just going to be the treated minus the control. My N is the length. And then I'm going to get my square root of N. I'm going to just call that Sn so I don't have to compute it again. Or actually, I think, yeah, sorry, I could just take that out because I do compute it. So now I've got this. And so what I do is I get the product of these things. And that's going to give me, again, this list of positive and negative ones. So the very first one is going to be all ones, and then one negative one somewhere, then two negative ones somewhere, and then all the way down to all negative ones. And I'll turn that into a list and then make that into an array. So this X now is just going to be 2,048 sets of 11 numbers of ones and negative ones. And I'm going to take my X, or sorry, take this X, I'll multiply it by my D. And so this now, my exact, is going to use broadcasting, and I'll have that entire list of possible weights that I could have possibly observed under my assumption of the null hypothesis. And now I'm going to get the distribution. So I'll just get the distribution of my test statistics. So I'm going to get the mean of my exact. I'm going to divide it by the standard deviation divided by the square root of the number. Right. So now this is the under the hypothesis condition on my data. This would be the distribution of the test statistic I would expect to observe. Simulated version, same sort of thing. Now what I'm going to do is I'm going to take a binomial. So this will be a sequence of zeros and ones. I'll take 2 times it. So now I'll have a sequence of zeros and twos. 1 minus the 0 is going to be a 1. 1 minus the 2 will be a negative 1. So I'll get my net ones and negative ones. Now I'm just going to reshape that into the shape I want. Again, because it came out differently, I have to transpose it now. But again, this is what my exact was before. And now I get my simulated means and my simulated standard deviation divided by the square root. So this would be the distribution under the sampling, the previous one under distribution under the exact. And then to get my, my p-value, I'll just get my observed test statistic. So this is the original differences, the mean divided by the standard deviation divided by the square root. And I'll look at the number of instances of that distribution that have a larger or equal observed t-statistic. Again, I'm one-sided, so I'm looking just at larger. And I'll get the mean of that, which will give me a proportion. And so now I've got a p-value of 0.0009. And just to compare it, so here, typically with the hypothesis test, you choose some cutoff. In this case, both of these, if you use the standard cutoff, would have been reject. But you can see the real point here is not whether you reject or accept, but this is a fairly different p-value. And I could probably cook up an example where, in fact, I know I can, because I've got examples where the asymptotic one doesn't reject when the other one does. So now, if we just want to visualize this, so what I'm going to do is now I'm going to get matplotlib and numpy and scipy, and I'm going to get a histogram of my distribution. So again, I'm going to use my exact distribution. I'm going to have 100 bins, and I'm going to normalize it. So instead of being pure counts, it's going to be frequencies. I'll get my, here what I'm taking is my observed t-statistic, and I'll draw a red line at that point. So that'll be that 3 point whatever. I'll get my degrees of freedom, and I'll get a linear space, and then I'm going to plot now my t-distribution on top. So we'll look at that. And so here what you see is this histogram is the exact distribution of my test statistic conditioned on the data I observed under the assumption that the null hypothesis is true. This little green line, which you can see, is the actual t-distribution that we would have used as a parametric test. This line here, which should be red, is the cutoff. And you can see right away the exact distribution has a much centered peak. It goes outside on the end and it comes down. And right, if you remember your binomial, the very first one's going to be a triangle function. And this triangle function, as you increase the size of your binomial, will eventually approach normal. But in the meantime, until it does that, it's in here, which is normal. Right, so I try to draw it here, but on the tail it's going to be under, in the middle it'll be over, under, and then over again, which is exactly what we observed. And you can also see that where we have the cutoff, there's a lot more, I mean, if you can see, there's like that green line for the t has a lot more mass out here than we have on our exact distribution. So just to conclude, I have a permutation package that still under a year in development. GitHub, it's called Permute. I don't know if you can see this, but it's passing all its tests and has a fairly good coverage rate. There's a website mailing us. There's some source code and bug reports. It's also on PyPy, so you can just pip install Permute. It's fairly early on, so we basically have 1 sample, 2 samples. We have some tests for the simple linear regression. And then finally, I just want to thank my collaborators. So that example I showed was from Philip Stark. He's the driving force behind this. He was the chair of the stats department up until last year when Michael Jordan took over. And he's a huge proponent of permutation testing and resampling methods. Kelly is a student of his. She's done a lot of the heavy lifting on this code. Stefan Vandervolt is a good friend and one of the core developers of scikit-image, contributed to NumPy, and he's also been helping out. And with that, I'd like to thank you and get the next speaker, or I guess see you soon if you have questions first, perhaps. Thanks.
So I think we have about 3 minutes for questions. We're taking 5 minutes of your tea time. So any questions?
How can we decide confidence interval? Like we assume it to be 5%.
Yeah, so for the confidence interval, you have to do some extra assumptions. So if we assumed, say for an example, a shift model, I won't go through quite the details, but I'll give you a hint. So the situation was under our null hypothesis, we were able to permute or relabel everything because it was a 0 difference. But if we assume that essentially that all the animals under control would be some C, and that T is just C plus a constant number over all pairs, then that D we can estimate by the mean difference, and then we can subtract those and relabel everything. But you have to have something. You can also do like so that's a shift model or an additive model. You could also have this be a factor, so it could be a multiplicative factor of the size of C. So instead of that, as a treatment, you assume 1 point something. If you're assuming an increase. But typically for confidence intervals, you have to make some additional assumptions. Often the p-value is easier to get. And again, as soon as you start making additional assumptions, you're going to have some more questions about whether they're real. And you have to justify this, at least in my mind, by the scientists and the scientific expert knowledge of the field.
Thank you, Jarrod. Really nice talk. The question is for both you and as well as Andreas. So I'm in the field of satellite imagery analysis and all that. The problem we are facing is that there are there's thankfully in Python, scientific Python, there are many packages. There's an entire ecosystem of pandas, skitlearn and all that, which is helping us do stats on spatial data. But does your package or is Andreas looking into including statistics with GPUs or parallelism in statistics so that we can do better stats on spatial data, on large amounts of data using new technologies?
Yeah, so that question was, how does some of the stuff work with GPUs? And my code, so it does, but I can answer.
Well, what I'm going to answer is I wish I understood more of statistics, and if you have needs in terms of where you think here's something that my stuff could easily include. If I had known about it, just tell me. Tell me what you need, and I might be able to make it happen fairly quickly. That's the best I can offer.
Thank you.
Yeah, before we break, I really like everyone to know more about permutation tests and statistics in general, and I would heavily recommend going to Ani Adhikari's lectures. She's a really great lecturer, and she's a pleasure to listen to, very clear, and I think those lectures would be a really great way to get started.
One last question.
A basic statistics question. What is the difference between independence and non-interference?
Independence and non-independence?
Interference. Non-interference.
Maybe we could take that offline. I'm not quite sure I can give a very succinct answer to that. Independence is a much more easy idea from probability, where interference I feel like has a little bit more scientific influence, and I'm not clear on interference. Yeah.
No, here in his talk.
Yeah, I mentioned it.
Oh, okay.
Yep. Yeah. Okay. Maybe offline. But yeah, independence is a much easier thing. Or at least for me it is.
Okay. So with that, we break for tea. Please be back by 11:15. Sorry, 5 minutes of your tea time.
Yeah. Yeah. I didn't say much about it.